Hello learners, this class is for second year 4th sem optics paper inference chapter and the topic name is oblique instance of a plane wave on a thin film due to reflected light, or it is also known as cosine law. Okay, oblique instance of a plane wave on a thin film due to the reflected light. Now interference due to reflected light. Now I'll show you the diagram. Here let G1 H1. So see here G1 H1 and GH. Okay, these both are the two surfaces. Okay, let these two are the two surfaces of a transparent film which is having uniform thickness T. Okay, uniform thickness T and refractive index is mu. Okay, so refractive index, let it be some mu. Suppose a ray AB is incidenting on the upper surface. This is the ray AB that is being incident on the surface. This ray is partly reflected along BR. Partly reflected along BR. After that, it is also transmitted along BC. Like here. It is transmitted along BC also. Now, after one internal reflection, here goes the internal reflection. Here goes the internal reflection. Okay, internally it is reflecting. So after internal reflection, what happens? You can see after internal reflection at C we obtain the ray CD. Okay, this one we obtain the ray CD. After refraction at D, at here, the ray finally emerges out along DR1. Okay, this is DR1. Okay, DR1. It is emerging out from the surface. So obviously DR1 is parallel to BR. Okay, DR1 is parallel to BR. These two are parallel lines. Our aim now is to find out the effective path difference between these two rays, BR and DR1. What is the effective path difference between these two rays we are going to find out. So for this purpose, we have to draw a normal DE. Okay, let us draw a normal DE. DE. Where? On BR. Okay, we have drawn DE normal on BR. And we are also drawing normal BF. Normal BF, you can see BF on DC. DC. We also produce DC. That means we also extended in backward direction till P. The optical path difference between these two reflected light rays BR and DR dash is given by, now let me write here. So did you understand? We are going to find out the path difference between these two lines, these two rays. So the path difference will be, you can see, the optical path difference between these two reflected light rays BR and DR dash or DR1 is delta is equal to BC plus CD, that is BC plus CD, the refractive index, mu BC plus CD in film minus path of BE in air. Okay, so mu of BC plus CD minus B is refractive index of air, that is 1. Now we know from Snell's law mu is equal to sin I by sin R. So little bit when we see the trigonometrical ratios, that means from triangle BDE, once you see the diagram, from triangle BDE we can get sin I is equal to BE plus BD because opposite by hypotenuse. So from triangle BDE we get opposite by hypotenuse as BE by ED, and we from triangle BDF we get sin R as FD by BD. Okay, so we'll substitute here. BE by BD, FD by BD. BD cancels. So what remains? BE by FD. Mu is equal to BE by FD. So how we can write this? We can write BE is equal to mu FD. Okay, mu FD. Let this be equation number 2. This is 1. So when we put second equation in first equation, we get del is equal to mu BC plus CD minus mu FD. Okay. Now from the diagram, we can write CD as CF plus FD. So once you check in the diagram, CD we can write it as CF plus FD extended one minus mu FD. So mu BC plus CF plus FD minus FD on taking mu common. FD cancels out. What remains? Mu into BC plus CF. So from the diagram again we can write BC plus CF as PF. Okay, let this be equation number 3. And again when we go to the diagram, we can see from triangle BPF that cos R is equal to PF by BP. That is adjacent by hypotenuse. PF by BP. From triangle BPF we can write like this. Cos R is equal to PF by BP. And again we can write PF is equal to BP cos R. And what is BP? BP is 2 times the thickness. So 2T. You can check in the diagram. BP is 2 times the thickness. 2T cos R. Okay, if you want me to check, I'll check here for you. So you can see this. BP. This is 1T, this is 1T. So thickness is 2 times 2T. So PF is equal to 2T cos R. Let this be fourth equation. Now we have PF in the third equation. So in the place of PS, we'll write 2T cos R. So del is equal to mu 2T cos R. Or you can write 2 mu T cos R. This is the path difference between that two rays. Okay, on reflecting, one after reflecting, one after internal reflecting. Between that two rays, we have found out the path difference.